Hi and welcome to our new session here on acquisition function optimization. So, in each iteration of our, Bayesian optimization loop, we've now learned that we exchange the optimization of our very costly C, cost function, to the optimization of our acquisition function U. These two optimization problems have many similarities, and specifically we have to solve this second one here practically somehow. So I guess we should rather talk about this for a few minutes, how we can do that. So, and before we talk about what's an appropriate optimizer, usually it's a good idea to talk about the properties of the optimization problem you are facing. So these two, optimization problems have quite a few similarities. So first of all, obviously we are still optimizing over the same configuration space structure. The objective U also somehow, at least vaguely, looks similar to this C function. Well, it's somehow also shaped by this type of the acquisition function we're putting on top of it, but at least it has something to do with the cost function. The cost function structure is very complicated. I guess the U structure will also look quite complicated. We will see that it might, in most cases, it looks more complicated than the structure of C. I'll have some visualizations on some of the upcoming slides. So these are all bad news, so nothing has really changed. So have we really done something intelligent by going from C to U? Well, yes. U, as we've discussed before, is now cheap to evaluate. So we now only have to query the model. Yes, it's posterior means, posterior uncertainty, instead of this costly C. And this is exactly why we call this a surrogate, right? So it's an alternative, a cheap alternative to the cost function that we're now optimizing. We are still facing a non-trivial multimodal problem. See this in visualization in a few minutes. Maybe this is a differentiable problem. Maybe it's also on a complicated configuration space structure, with, mixed stuff and hierarchical stuff in there. I'll now talk a little bit about how we can, numerically solve that. It's a little bit debatable how perfectly we have to solve this problem, because our surrogate is only a coarse approximation of reality. We could say we want to optimize this as much as possible to place our point as optimally as possible, but on the other hand, we haven't seen too many design points, especially in the beginning of the optimization. The model will not be perfect, so it's a little bit unclear how much budget we want to spend, how much overhead time we want to spend on solving this quite hard problem perfectly. Before we talk about concrete optimizers, how about we take a brief look at the acquisition function landscape. So this is usually non-convex and multimodal. So I've already said for EI and PI, for training points and the noiseless interpolating regime, this will be 0. It peaks somehow between them or close to them, but the landscape gets more rugged as the surrogate is fit to more data. And you can see this here below. So especially in high dimensions, you get like structures where you have like very flat plateaus with narrow peaks between them. This begins to look something like a dreaded, sometimes these functions are called like hedgehog functions. You have these very, very small peaks on very flat plateaus, and optimizing stuff like that is not easy. At the very least, this stuff here is multimodal. So just running local optimization once is usually not a good idea. There is one extra trick you can employ to make acquisition function optimization a little bit more well-behaved, and that's usually a good idea from everything that I have seen in practice. So I guess you nearly always want to do this, I would say. So you usually optimize your acquisition functions on a log scale. And there are two ways of doing that. Confusingly, they are sometimes called nearly similarly. So I'm mainly talking here about the EI, so the expected improvement. So there's the log EI for numerical stability. This is not, rocket science what happens here. So we just take the EI and we optimize it on log scale. And you can now, look into how to do this in a numerically extremely stable fashion. So in this paper here, they have shown how to do this very nicely via stable log space arithmetic by using, special, logarized components, so to speak, in the computation, and that gives you a very stable evaluation of the log EI, and that is also an available trick that's implemented in BOTORCH, and a similar thing is usually implemented for many other acquisition function types, and that resolves the problem of having these like zero plateaus in areas where the acquisition function is mathematically maybe not exactly zero, but it becomes numerically nearly zero. So I guess it's just a numerically more well-behaved version of your EI. And I mean, of course, you can optimize that on log scale, because it's just taking the log is just a simple monotone transformation. So you get the same proposed point as if you would optimize EI in theory, right? And in practice, you usually get something which is, I don't know, numerically a bit better. You can also do something else, and this is doing log EI on log transform targets. So in that case, you would actually train your surrogate model on log C cost values. So you log everything in your archive, you log the costs, and then you train your surrogate model on that. And that's actually a very old trick for regression models, where your regression model assumes that your outputs are somehow normally distributed. Yeah, and that's exactly, I guess, what we're doing. If you're using a Gaussian process, and if you have like these if you have heavy right tails in these distributions, you observed C values, and that's actually something that happens very often in AutoML, HPO, and algorithm configuration, then this logging of the cost values repairs this. And then what you can do is you can actually write down an analytic formula for your expected improvement criterion on the original Y scale. You get this, again, nice closed form formula here, and you can optimize this guy here instead of the normal EI formula that I've shown before. And that is usually a good idea. This, to my experience, works quite well in practice, especially because you're repairing also a problem in your surrogate model and not a numerical problem in your acquisition function. Okay, some comments on how we can now, as I said, I wanted to discuss how we now optimize these acquisition functions in practice. So first option, we just do random search. So some people do this just because it is extremely simple. They just sample, I don't know, a few thousand or 10,000 points and then take the best. Especially also maybe because of this, we do not have to optimize the acquisition function perfectly in every iteration. Is likely not a good idea in higher dimensions, and we maybe want to do this, go about this in a somewhat more intelligent fashion. So I guess the next option is to run some local optimizer on a numeric space. So you can run something that's like gradient based, but you can also run a quasi-Newton technique like BFGS, and that's actually implemented in many toolboxes. So you can use BFGS here, or I don't know, the constraint version on box constraints, so LBFGSB, and because of the multimodality, because of the non-convexity, usually you combine this with a simple restarting technique. So first of all, we can discuss whether we can run such gradient-based optimizers anyhow on the acquisition function. The answer is often yes. So we need, of course, now the gradient of U. Well, the good news is for standard kernels, our Gaussian process is usually differentiable. So you can take the derivative of our GP model with respect to lambda, but you can also usually take the derivative with respect to lambda of the acquisition function itself. So if you combine a Gaussian process with a, I don't know, standard kernel, so to speak, on a standard acquisition function, you can simply compute gradients in analytic form. And then you can run with such a gradient-based optimizer on this. You could also estimate gradients, but then you have to invest a little bit of extra overhead time for the estimation of the gradients. And if you can do this analytically, this is a bit nicer. Also, if you want to have something without gradients, there's also CMAES on numeric spaces. So CMAES is for covariance matrix adaptation evolution strategy. So from that name you can see, well, it is an evolution strategy. Because of that, it's population based, it's gradient free. Actually, it's something that we would call an estimation of distribution algorithm. So in each generation, so in general, CMAS maintains a Gaussian distribution that is, well, parameterized by a mean vector and parameterized by a covariance matrix. Okay? This mean vector is supposed to be placed somewhere in configuration space, in search space, and we now want to move that mean vector closer and closer and closer to the optimum. But we also have this covariance matrix structure, and this is also adapted while CMAS runs. And the idea is, in a certain sense, for this covariance matrix, I guess, to reflect second order information, so to reflect the Hessian structure of our underlying objective function that we're optimizing. And this adaptation, so how does CMAS, I don't know, the most basic loop of the optimizer looks like? So we have this multivariate normal distribution here. We sample candidates from it. And you can see this also here on the right-hand side in this plot. So we have generation 1, which is green, and generation 2, which is in red. And you can also see here the mean value for the first generation and the covariance structure for the first generation. Here you can see the mean value for the second generation and the adapted covariance structure also for the second generation. So currently we are, I don't know, maybe in the first generation. We have our Gaussian here in front of us, and now we sample candidates from it. And these candidates get evaluated by the objective. They get ranked by their fitness. And then we take the best, we kill off the worst, and we update the mean vector only with, I don't know, something like the best half of the evaluated candidates. And we also update our covariance structure from these best candidates. And then we shrink also this sigma squared weighting factor here in front of the covariance matrix. So the nice thing about this is that because of this mechanism that, I don't know, our C function, our C capital C covariance matrix learns the local curvature. So it imitates something like a second order optimization procedure, potentially based on the second derivative, based on Hessian information, without directly computing that or even having access to first or second order gradients. This is quite robust on non-convex and even ill-conditioned functions. It's constructed exactly for these cases. But once we start contracting this, I don't know, factor sigma here in front of the covariance matrix more and more and more, we enforce convergence, local convergence. And this is, in a certain sense, something that we want, so that we converge to a point at the end. But on the other hand, now the search becomes effectively local. So we can, I don't know, jump around the input space, the search space a bit, and we can also leave local minima to a certain extent. But at some point, we will contract and converge to something that's local, and we will not be able to escape that completely. And because of that reason, CMAS is usually also combined with restart techniques. So there's something like IPOP CMAS and BIPOP CMAS, where they're trying to, I don't know, detect good, I don't know, points, time points where you should stop the optimization because you're not expecting any progress anymore. And then you're restarting, and you're also then changing your population size. So you're doing runs with larger or smaller population sizes. So for IPOP, you pretty much just increase, you double your population size, while for BIPOP, you have like a balanced schedule, so to speak, where you have like smaller and larger population sizes going on. Can we do something also for mixed hierarchical configuration spaces? I guess that's the most challenging scenario. So in these cases, you usually run something like a repeated one exchange local search on the mixed hierarchical space. So how does this look like? Well, you run multiple local searches, but you run them in parallel with this one exchange, I don't know, terminology. I mean that. So, okay, how does this local search work like exactly? So we are at some point, and we now want to produce multiple neighbors in the vicinity of that point. I guess that's what the local is all about in the local search here. And we will do this by changing simply one component of our lambda candidate. And we now look at the data type, so to speak, of the decision variable. So this can be categorical, this one, and yeah, okay. So we generate multiple neighbors around the lambda, but for each neighbor, only one hyperparameter gets changed. Yeah? So we only change one dimension of this lambda candidate, yeah, to, I don't know, create, I don't know, variations, so to speak, around it. So we do and we do this by looking at the data type of the hyperparameter that we are randomly choosing to change it. So it could be categorical. Okay, then we just like randomly flip the categorical level. It could be a numeric or an integer parameter. Then we perturb the current value by adding in a little bit of Gaussian noise. And if this is an integer parameter, at the end, we round to the nearest integer value. And if we have conditional hyperparameters, it's a little bit more complicated, but not that much. So we would only mutate children of active parents, and everything else we would not allow to mutate. And if, I don't know, some parent parameter gets activated or deactivated, then, I don't know, we activate or deactivate the children accordingly. So in a certain sense, if we have this, I don't know, tree structure of the hierarchical dependencies, and if we change something like here, we in a certain sense repair everything that's down here below. And after we have produced for one point lambda in our local search a bunch of different neighbors, we evaluate all of them, and then we move to the best one. And if there wouldn't be a best one, and all of these neighbors would stay at that point and just try it again. But assuming there is a better neighbor, we move to it, and then we iterate, do it again, do it again, do it again. And at some point, if there's not enough progress, we might also restart such a local search. And in general, because of the multimodality of our acquisition function that we now discussed a couple of times, there is also kind of a restarting. Well, there's also, we would even run multiple of these local searches in parallel. Yeah? Also for, I don't know, implementation reasons. So it's nice to have a couple of these local searches running in parallel, so to speak, so that we can evaluate multiple, as many points as possible in terms of the prediction of our surrogate model. That usually reduces overhead in the evaluation. Okay, we've also reached the end of this session here. So let's do a quick summary. So proposing a point in the acquisition function or via the acquisition function is itself an optimization problem, but it's based on a cheap surrogate. Our acquisition function is usually non-convex, it's usually multimodal, usually gets even more rugged with data. For numerical configuration spaces, very often we use something like BFGS with gradients and with restarts, or CMA usually also gives you good results. Again, with restarts. And for mixed hierarchical spaces, usually do this SMAC style iterated local search that I've described a few minutes ago. For multi-starting, and I guess that relates to all of the techniques I just referenced, it's likely a good idea to start at least some of these multi-starts from good design points that you've seen in the past, because of exactly this structure here. So maybe these peaks are, I don't know, at least close to the design points, and it's a good idea to search from something. I guess we want to, maybe it's also a form of, I don't know, baking in a little bit more exploitation. I guess it's a good idea to search around what we have evaluated before, at least for some of these multi-starts. And I've already said it's a little bit unclear how perfectly we have to solve this inner optimization problem, how much computational overhead we're willing to spend on that. It's not going to come for free. So I guess that's a bit unclear. Yeah, usually we do this until we don't see enough progress anymore. Okay, this concludes this session here. See you in the next one.